Hi everybody. I want to get a little practice in for the final exam. I got 3 little videos about that. This is going to talk about the part of the final exam that deals with the right triangles. As we go through this, I may not work it all on this page. I got some paper I can pull in, but you want to collect a page of formulas that you're going to use during the final exam. I'll allow you to have one page of your own handwritten work that you can bring to the final exam and keep on your desk during the final exam. And it will relate to all these kinds of questions, I figured. Let's work through the first one. Got a right triangle and an altitude drawn to the hypotenuse. If AX were 6 and XB were 9, we're going to have to either figure either CA or CX or CB. We've got to find these different lengths. Allow me to call this one X and that one Y and that one Z. And it'll be easy to talk about them that way. I would like you to remember that these are each geometric means. They would appear in both of the means positions. We could talk a lot about it, but I'm going to tell you how it works. In this figure, X is a geometric mean. I put it in both of the means positions. Between its part of the hypotenuse, 6, and the entire hypotenuse, that's 15. And you just cross multiply and solve that out, and that would give us X squared is equal to 90. Take the square root of both sides, and X is equal to, what do you know about the square root of 90? It is 9 times 10. I know the square root of 9, so that would have been 3 root 10. So that would have been the length for AC. This segment in the middle. You know, there are these 3 sketches that we ought to make, that I would make if I were making my review for the final exam with that right triangle right there. With an altitude drawn to the hypotenuse, and say that this segment is the geometric mean between its part of the hypotenuse and the full hypotenuse. That's the problem I just exhibited. And I can make 3 sketches like that. You might recall them. The altitude to the hypotenuse. This segment is the geometric mean between the 2 parts of the hypotenuse. That's how we're going to get CX. CX, the thing we labeled as Y here, is the geometric mean between the 2 parts of the hypotenuse, between 6 and 9. That's what this sketch would indicate to me with 2 bars. This is the geometric mean between those lengths. And when you cross multiply, we're going to get Y squared is equal to 54. Take a square root of both sides, and you know any perfect squares that go to 54? And I say, well, it is 9 times 6. And I know the square root of 9, so we're going to get 3 times the square root of 6 for CX. And then, like the first figure, this length over here, Z, is also a geometric mean. Z is the geometric mean between its part of the hypotenuse 9 and the full hypotenuse 15. As we cross multiply there, we're going to get Z squared is equal to, and that's 9 times 15 is 135. Take a square root of both sides, and the square root of Z squared is just going to be Z. But what about the square root of 135? Well, it is 9 times 15. I know the square root of 9, so that'd be 3 square roots of 15. Getting a little bit crowded on this page. I'm going to pull another piece of paper in. I think you're going to want to do that too. After working with a geometric means, I'm going to have to work with the Pythagorean theorem with ugly numbers like legs of length 3 root 3 and 3 root 6. So I got a right triangle to say with legs of length 3 root 3 and 3 root 6. And this is just a little warning, a heads up. Hey, you're going to have to work with the right triangles like this. But that shouldn't be a big problem. We'll use the Pythagorean theorem. 3 root 3 squared plus 3 root 6 squared ought to equal the hypotenuse squared. When you square these, we ought to square both parts, and when you square the 3, you get a 9. You square the square root of 3, you get a plain old 3, so 3 root 3 squared is 27, plus squaring both parts here, the square of 3 is going to give me 9, the square of the square root of 6 is just 6, and 9 times 6 is 54. Happily, those add up to 81, don't they? Is equal to 8 squared. So the hypotenuse must have been 9. There's another question like that. Or a hypotenuse, another right triangle setup. A hypotenuse of length 4 root 6 and a leg of length 4 root 2. I guess we're going to find the length of the other leg. I'll call it A. And hit that with the Pythagorean theorem. Have to be A squared plus 4 root 2 squared. And that's the trick. You got to square those funny looking numbers. Would equal to 4 root 6 squared. you're going to have a squared, and squaring this, you're going to get 16 times 2. 4 squared is just 16. The square root of 2 squared is a plain old 2, and that's 16 times 2 is going to give me 32 is equal to, and this will be 4 squared 16 times, and the square root of 6 squared is 6, so 16 times 6 is going to give me 96. Subtract 32 from both sides, and I got a squared is equal to 64. So I'm saying a would have been 8 in this triangle. That leg would have been of length 8. You're just going to work through these. I may need another different piece of paper. Get to know the main diagonal of a rectangular solid. And this is a nice set of numbers here. It gives me a width of 8. I'll declare that to be 8. And a height of 6. We might talk about that cube in a moment as well, but let me work with the rectangular solid first. And a length of 24. And it asks me for the length of the main diagonal. Let me show a main diagonal. And there's a nice way to work it. There's a quick, easy way. We'll talk about both of them. That's a main diagonal. It's the hypotenuse of a right triangle. Let me see if I can't show that well. I'm going to try to show darken a triangle that would have that hypotenuse. I'm going to use a diagonal on this edge, on this face, to make that right triangle. And that would give us the length of the main diagonal if we set up that triangle right there. And you might see already, this is a Pythagorean triple, that 6 squared plus 8 squared is going to make me think that that length right there would have had to have been 10. Because I know that 6 squared plus 8 squared equals 10 squared. And this length being 24, I can work on that right triangle, and it would go like this. 6 squared plus, 10 squared plus 24 squared would equal the hypotenuse squared. That's looking like a glorified 5, 12, 13 triangle. I'm thinking h is going to be 26. So this is 100 plus 24 squared is 576 is equal to the hypotenuse squared, and that's 676 equals the hypotenuse squared. Take the square root of both sides, and that's 26. So I would tell you that's the length of the main diagonal there. And you could have done it a different way, quickly and easily. It would have been the square root of the length squared plus the width squared plus the height squared. That's going to give us that same amount. Let's walk through that and see that that is true. Length, it could go in any order. So length squared, 6 squared plus 8 squared plus, in the other dimension, 24 squared. Add that up and you're going to get 36 plus 64 plus 24 squared being 576. There gives me a 100, the 36 and 64 plus that 576, give me the square root of 676. And that's still that going to give me that 26. So there's the down and dirty way to remember it, the square root of the length squared plus width squared plus height squared. About that cube, we have to talk about that. With any cube, they're going to be similar to one another. What works in this one will work in that one. And it's a kind of a nice set of numbers. I'll show you what I know about it. Let's say that each side of this guy was 6 on this cube. How long would a face diagonal have been? And that gives you 45, 45, 90s. That's not beautifully drawn, but that would have been 6 times the square root of 2. And with this edge being 6 and that length being 6 square roots of 2, that hypotenuse is the main diagonal. Turns out it's going to be 6 square roots of 3. See that that's true. 6 squared plus 6 square roots of 2 squared would equal the main diagonal squared. There's 36 plus, and when we square this, we're going to get 36 times 2. That's 72 equals the main diagonal squared, and those add up to 96, which is 36, no, those add up to 108, excuse me. Those add up to 108, which is 36 times 3. Take the square root of both sides, now I got 6 square roots of 3. That happens for every cube. That is to say, if you had a cube whose sides were of length x, use the Pythagorean theorem as much as you'd like. If the sides are of length x, then the face diagonal, x squared, x square roots of 2. And the main diagonal, x square roots of 3. Always going to work that way. Let's look at another one. The sides of a triangle and decide if it's acute, right, or obtuse. Well, I don't think we've done enough of that this year. The converse of the Pythagorean theorem says if a squared plus b squared is equal to c squared, then that's a right triangle. But what if they don't add up that way? For example, if the sides were 6, 12, and 14. And I think to myself first, if it did have a hypotenuse, it'd have to be that 14, it'd have to be that biggest side. But let me walk through this with you. 6 squared plus 12 squared equals to 14 squared. I'm just asking that question. I don't believe that it's true. That'd give me 36 plus 144. And 14 squared is 196. These add up to 180, which is in fact less than 196. So no, sir, this is not a right triangle. So is it obtuse or is it acute? And here's the trick. That 14 is too big, isn't it? And if this thing is too big to be a hypotenuse, then it opened too far and it's obtuse. So the thing you would want to remember, if a squared plus b squared is equal to c squared, man, you got a right triangle. But also, if a squared plus b squared is less than c squared, then c is too darn big. It's longer than the hypotenuse could have been. Therefore, this angle has to be greater than 90. That forces it to be obtuse. And then there's another option, huh? What if the sums of the squares of the two smaller sides, a squared plus b squared, is greater than c squared? Then c is not big enough, and it would in fact be acute. That's worth remembering. I think it happens on your final exam. We got sides here of like 7, 9, and 12. I'm going to check on the 7 squared plus 9 squared. Does it equal to 12 squared? I don't think so. I'm asking that question though. And there's 49 plus 81. That adds up to, and we're asking, does it add up to 144? And these add up to 130, which is less than 144. So we got another obtuse triangle, don't we? I was kind of expecting it to be acute just because the first one was obtuse, but we got another obtuse triangle there. A squared plus b squared was less than c squared. Yep. Gotta know my way around a 30, 60, 90. And here we're supposed to give the perimeter. I think I might do that on another piece of paper. It looks a little bit crowded on this page. Here we got a 30, 60, 90 triangle, and the longer leg is known, isn't it? It's of length 9, opposite the 60. And first thing I got to do is go from the longer leg to the shorter leg, and to do that, what I got to remember about a 30, 60, 90 triangle, I got to memorize this fellow right here. Opposite the 30, the short side 1, the hypotenuse is twice that length, 2. Opposite the 60, we'll get the longer leg, which is the square root of 3. The way you move through this triangle is the way you move through this triangle. To go from the longer leg to the shorter leg, what do you do with that number to get to this number? I got to divide by the square root of 3. 9 divided by the square root of 3 is going to give me 3 root 3. And I would double the short side to get the hypotenuse. That'd be 6 root 3. So if somebody asked me the perimeter of that triangle, I'd give it to them. I could add, that 9's got to go by itself, but I can add the 2 root 3, the two sets with root 3. We would have 9 plus 9 root 3 for the area of that triangle. Let's do the next one. It's another 30, 60, 90 I see. And this time they're giving me the short side, which is 4 root 3. If I say that's a short side because it shows me this is a 60-degree angle, that must be a 30. I double the short side to get the hypotenuse every time, 8 root 3. And to go from the short side to the longer leg, I got to multiply by the square root of 3. And 4 squared to 3 times the square root of 3 looks like 4 squared is a 9. But the square root of 9 is just 3, so that's 4 times 3, there's 12. What about the perimeter of that triangle? Now I can add these numbers, and I've got to keep that guy by himself. So 12 plus 12 root 3. Interesting, kind of looked like the other one, didn't it? And give the perimeter of this interesting figure. Let's check on that. Looks like a square abutted to another 30, 60, 90 triangle with a 60 right there. And they give us the diagonal of the square to be 12. I know in that square I got a 45, 45, 90 with a hypotenuse which is 12. What I got to remember about the 45, 45, 90? Isosceles right triangle. The sides are in the ratio 1, 1, and the square root of 2. The way I move through this triangle is the way I move through this one. To go from the hypotenuse to the congruent sides, I got to divide by the square root of 2. So 12 divided by the square root of 2 gives me this length to be 6 square roots of 2. That would have also been this length, 6 square roots of 2. Opposite sides of that square are going to be congruent. And let's think, looking about this triangle, I'm thinking that that was a 60 here, therefore 30 there. Let's double that short side to get the hypotenuse. That'd be 12 square roots of 2. But what about this longer leg, huh? Well, I got to take the short side and multiply by the square root of 3. 6 square roots of 2 times the square root of 3. That's going to be 6 square roots of 6. Yeah, the outside guy with the outside guy, that's a 1. Inside guy with the inside guy, I can move those. And if I'm going to get the perimeter of this figure, I guess I'll go ahead and get that. The perimeter of triangle ABC is what it asked me. This was A, and there's B, and there's C. And I can add up those sides. I think I got to recognize that this length would have been 6 root 2 right there. That's a pretty good looking perimeter of that triangle. I would have 12. No other whole numbers, huh? Plus, this 12 root 2 could go with that 6 root 2, and that would be 18 root 2. Plus that 6 root 6. I think that's the perimeter of triangle ABC. That's a pretty good question. Work with 45, 45, 90s. Give the perimeter of a square and find the diagonal, or the vice versa. So if you had I might work this on another piece of paper. If you had a square with diagonal of length 28, go from the length of the diagonal to the congruent sides in a 45, 45, 90. I'll have to divide by the square root of 2. And 28 divided by the square root of 2. Practice that for a little bit. You get 14 square roots of 2. That's what this length would have been, 14 square roots of 2. In fact, all the sides on that square would have been. Give the perimeter of the square. And we can add up those 4 things. And 4 times 14 is 56 square roots of 2. Okay, and then if we knew the diagonal was 3 square roots of 6, that's going to be a little more interesting, isn't it? If the diagonal is 3 root 6, I'm still going to work it the same way. To go from the diagonal to one of the sides on the square, I'm going to divide by the square root of 2. So I have 3 square roots of 6 divided by the square root of 2. And I think there's a way we can clean that up. Just checking that I got that right. Yep. Actually, the quick deal would be the square root of 6 over the square root of 2 is just equal to the square root of 6 over 2. The quotient of the two radicals is the radical of the quotient, and that's just going to give me the square root of 3. So I have this 3 times the square root of 6 over the square root of 2, which just gives me the square root of 3. So 3 root 3 is what these lengths would have been. So to divide that by the square root of 2, you get this amount. 3 square roots of 6 divided by the square root of 2 gives me 3 root 3. Yes, you could get the perimeter of that square. It would have been 12 root 3. Just 4 times that amount. Lots of things about right triangles to remember, huh? Find the length of the altitude, apothem, median, and angle bisector in an equilateral triangle with perimeter 36. Let's see about that. If I had an equilateral triangle, perimeter 36, I might just do one of those and do another one in class if you wanted to, but with perimeter 36, each of the sides would have been 12. How long would the altitude have been? I might do a separate one for each of those, and the altitude shows for me right there. That's a 30, 60, 90 triangle. Short side would have been half the hypotenuse. There's 6, and the altitude would have been 6 root 3. Apothem. Let's get a look at the apothem of that equilateral triangle. And the apothem we know is the distance from the center of any polygon, any regular polygon, to a side. So that's the apothem. I'm going to find its length. I'm going to work on that triangle. Still got a 12 on each side of this equilateral triangle. This length is 12, and I figure this has been bisected, so this would have been 6, and here's a 30-degree angle. So that 6 is the longer leg, isn't it? To go from the longer leg to the shorter side, I'm going from this side to here, I got to divide by the square root of 3. And 6 divided by the square root of 3 is 2 square roots of 3. Let's take a look at why that's true. 6 divided by the square root of 3. Let's rationalize our denominator. Multiply by the number 1. Square root of 3 over itself. This should not change this value, but it's just going to change its appearance. It gives me 6 square roots of 3. And when I multiply in the denominator, square root of 3 times the square root of 3 gives me a plain old 3. And that's 6 divided by 3 leaves me with 2 root 3. So we got the apothem, 2 root 3. It didn't ask me for the radius of the polygon, but that would be the radius if anybody had asked me about it. What else was I supposed to know about it? The apothem, the median, and the angle bisector. And actually, interestingly, this is a median. That altitude is also a median because it goes to a midpoint. That's all you got to do to be a median. And it's also an angle bisector, isn't it? So if somebody asked me about the length of the median or the angle bisector, I'd say it's the same as the altitude. It was 6 root 3. And I think that told us everything we need to know about the equilateral triangle with a perimeter of 36. And you could do it with one of length 15. I'm just not going to force you to watch me do it on this video. Let's do the next one. Oh, we're going to use a little trigonometry, huh? That's a nice thing to see. Let's work these out. Something you might want to sketch on your formula page that we're building. SOHCAHTOA, huh? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA. Looks like this hypotenuse is 60, and this angle is 25 degrees. They ask us to find AB and BC. Let's go for AB first. Just to keep it simple, I'm going to call it X. I'm thinking about SOHCAHTOA. I want to know the adjacent leg to this 25-degree angle in this right triangle. This is the adjacent leg, and that's the hypotenuse. So I got to use the one of these that represents adjacent and hypotenuse. That's got to be cosine. I'll make a couple statements about the cosine of 25 degrees, isn't it? Yep. And the cosine of 25 is adjacent over hypotenuse. And in this triangle, that would be x over 60. Then I just got to take out my calculator and ask my calculator after checking the mode real quick, and it has degrees, and I'm happy about that. What is the cosine of 25? And the cosine of 25 is 0.9063. Yep. Equals 0.9063 over 1. That's a proportion to solve. And I can see that it's just going to be 60 times 0.9063. I got the 0.9063 on my calculator still. I'm just going to multiply it with 60. And I'll say about 54.4. I'll round things to nearest 100. Nearest tenth, excuse me. 54.4. That's X. Now let's get this other length Y, did I call it? Yeah, we could call it Y, why not? That's CB. I would say I'm looking for the opposite length, but I know the hypotenuse. We should use the one with opposite and hypotenuse, and that's going to be sine. Let's make a couple statements about the sine of 25 degrees. Sine is opposite over hypotenuse. In this case, that would be y over 60. And we go to a calculator and ask for the sine of 25 degrees. And sine 25, 0.4226 over 1. Wanting to solve that proportion. 1 times y is going to give me 60 times 0.4226. With a 0.4226 times 60, I'll go for about 25.4. And that's a little bit of trigonometry that you have to do a little bit of that. Let's play a little bit more, see what else we can do. Here we see a 28-degree angle, and this length being 12. I can work that on this paper. Let's see what I can do. I'll do a little scribbling on another. We want to get QR. I'll call that one X. And we want to get PR. I'll call that one Y. If I wanted the hypotenuse X, I know the opposite length. I wish I had the hypotenuse. That's going to require sine, isn't it? Sine is opposite over hypotenuse. So I should make a statement about the sine of 28 degrees. The sine of this angle opposite over hypotenuse would be 12 over x. Then we go to the calculator and say, hey, calculate what's the sine of 28 anyway. And the sine of 28, I'm going to come up with, best I can see it, 0.4695. 0.4695 over 1. Be careful solving this proportion, huh? When you cross multiply here, 12 is equal to this times x. We're going to have to divide 12 by 0.4695. I got that on my calculator. I'll go kind of quickly. If I 12 divided by second answer, then that gives me about 25.6. else can we do? Let's we want to get another length, don't we? I just did get x, let's get y. If I wanted the adjacent length y to that 28-degree angle, and I know it's opposite and adjacent, there's tangent, huh? So the tangent of 28 is opposite 12 over adjacent y. Gonna figure out what the tangent of 28 is as quick as I could. Tan 28 equals, and give it to you at 0.5317 for the tangent of 28 over 1, and then scope out that proportion and decide what we gotta do. 1 times 12 is equal to this times y. We'll have to divide 12 by 0.5317. That'll give me the value for y. 12 divided by 0.1357, was it? Oh, gosh, got that wrong. 0.5317. There we go, and I'm coming up with 22.6. If I had a lot of extra time and I didn't mind boring you, I'd use the Pythagorean theorem, see if that worked out pretty good, but I think we're okay. We're going to find the measures of a couple of angles as well. Let's find the measure of angle A and angle B. I know that this is a right triangle. That's told to me already. So I could ask you, what do you know about the sine or cosine or tangent of angle A? You could do either one. But the sine of angle A is 7 over 25. And if you want to know the measure of angle A, you can arc sine both sides of this equation. The arc sine of the sine just leaves the measure of angle A equals the arc sine, let me write it carefully, of 7/25. And that's something I have to do with my calculator. The arc sine of 7/25. Let me show you carefully how that works. Second sine, and that gives me the arc sine. And then I'll just type in 7 divided by 25. And that tells me that angle is about 16.3 degrees. Let's go for angle C, is that angle B as well. I know these ought to be complementary, they ought to add up to 90, but let's just get a little practice in. Do you know sine, cosine, or tangent of angle B? You could do the tangent, you could do any one of the three, but I'm going to force you to do tangent. What would be the tangent of angle B? Opposite over adjacent for tangent, that would be 24 over 7. I should have written that better. The tangent of angle B is equal to 24 over 7. Let's arc tangent both sides of that equation, leaving the measure of angle B is equal to the arc tangent of 24 sevenths. Let's do that with a calculator, get a look. Second tangent, 24 divided by 7. And that gives me 73.7 degrees. Happy about that. 73.7 degrees. I'm seeing that these two angles add up to 90. So I'm happy that those angles were complementary. They had to have been. Let's look at another one that gets a little more interesting because it's got funny numbers, doesn't it? Let's work out and figure out the measures of these acute angles. You could do, well, actually with angle P, because I only know two sides, I'm limited. I only know for angle P it's opposite and it's adjacent. That forces me to use tangent. Tangent is opposite over adjacent, and the tangent of angle P would be 2 square roots of 7 over 6. Now I can reduce that fraction, and it probably behoove me to do so, just the square root of 7 over 3. And if I want to know the tangent of angle P, an arc tangent both sides, the measure of angle P will be equal to the arc tangent of the square root of 7 over 3. I gotta be a little careful how I enter that on my calculator. Second tangent, I did that wrong, clear that, second tangent, and then I gotta hit the square root of 7, and I gotta close my parentheses, you gotta get out of that radical, divided by 3. I think I got that written okay, the arc tangent of the square root of 7 over 3, and that's gonna tell me about 41.4 degrees, huh? Measure angle P, 41.4 degrees. Because we got some funny numbers, we want to go do that with angle Q as well, just to kind of get for sure that we got this right. And you could have to work with the tangent of angle Q. It would be opposite over adjacent. Opposite would be 6 over 2 root 7. And we could enter on the calculator that way. Well, let's rationalize some denominators, get a little play. That'd be the same as 3 over the square root of 7. If we were to rationalize our denominator, square root of 7 over the square root of 7, that'd give me 3 root 7 over a plain old 7. So the tangent of Q is equal to that. The measure of angle Q would be the arctangent of 3 root 7 over 7. Let's get a look at that and see if it is the complement of 41.4. Second tangent, what I want to show, and then type in 3 square roots of 7 divided by 7. I think I got it as I wanted it, and that's going to be 48.6 degrees.